Hello, welcome to another module in this massive open online course on probability and random variables for wireless communication. So, we are talking about random processes, and in the previous modules we have seen the properties of a wide sense stationary random process, and also more importantly we have seen the power spectral density, the definition of a power spectral density of a wide sense stationary random process, and an interesting application in the context of the bandwidth required for the transmission of a wireless signal, that is a spectrum that is required for transmission of a wireless signal, right. So, let us continue our discussion on random processes, and let us today look at the transmission of a random process through an LTI system, that is what happens when a random process is input to an LTI or a linear time invariant system. Okay. So, in today's lecture let us start looking at the transmission, another key property, that is the transmission of a random process through an LTI the transmission of a random process through an LTI system, where what is the meaning of LTI? LTI denotes, obviously most of you should be familiar with this, LTI denotes a linear time invariant. LTI denotes a linear time invariant system. So, what are we considering? Let us consider a wide sense stationary random process xt. So, let us start by considering xt, which is your W sense, which is what we have been talking about, which is your wide sense stationary, random process xt. Okay. So, xt is a basic wide sense stationary random process, and what we are saying is this random process xt is input to an LTI or a linear time invariant system, and remember every linear time invariant system is characterized by an impulse response. That is the key aspect of an LTI system, that is every linear time invariant system is characterized by an impulse response. Let us denote this by h t. So, we are saying this wide sense stationary random process xt is input to a linear time invariant system with impulse response h of t, and that I am going to represent that schematically over here. So, I have my LTI system, this is the input to the LTI system, and so I have an LTI system, this is the input, this is the output. So, xt is the input to the LTI system, yt is another random is the output of the LTI system. So, this is my LTI system, which is characterized by the impulse response h of t. Remember every LTI system is characterized by, so what is ht? ht is the impulse response of this system. So, this is an LTI system and this is a linear time invariant system xt. What is xt? xt is the input, yt is the output. xt is the input to this LTI system, yt is the output to the LTI system, and the LTI system is characterized by the impulse response h of t. That is, if the impulse delta t is applied as an input to this LTI system, then the output will be h of t. That is the meaning of the impulse response. That is, impulse response is nothing but a response to the impulse input of this system. Okay. And therefore, remember, for an LTI system, the output y of t for any signal input signal x of t, the output y of t is the signal x of t convolved with the impulse response x h of t. So, this is your convolution, this is your basic convolution operator, this is your input random process which is White's and stationary, this is your impulse response, and this basically y of t is the output of the system. So, the output of the system, the output of this system y of t is the input x of t of this system convolved with the impulse response h t of this system, and the convolution operator can be represented in the time domain as follows. So, I have y of t which is equal to minus infinity to infinity x of t minus alpha times h of alpha d of alpha. This is basically the convolution. So, this basically is your convolution, correct, and also we are given that this x of t, this is a random, this is a random process, this is random in nature, right. Further it is a function of time. Now, y of t is therefore it is random, since x of t is random, y of t is random. Also naturally y of t, you can see this is a function of time, that is it is random, it is a function of time, y of t is random because x of t is random, that is the input is random to the LTI system. So, naturally the output y of t is random, further it is a function of time, correct. So, y of t is random and is a function of time, that is it is indexed by time, therefore, y of t is also a random process. So, output y of t, the output signal y of t which is random and a function of time is a random process. So, this is also your y of t is also a random process, and more therefore, now what we would like to do is we would like to examine the properties, we would like to examine what are the properties, examine the properties of, we would like to examine the properties of, we would like to examine the properties of this output random process y of t. What are the properties of this output random process y of t? In particular, we would like to ask the question, is y of t White's stationary? If y of t is White's stationary, then what is the mean and what is the autocorrelation of y of t? So, we would like to answer the question, is this output random process y of t, is this also White's stationary? It is not a given that it is going to be White's stationary, we have to demonstrate that if it is White's stationary, which is what we are going to do next. So, now let us examine y of t. First, we have shown that y of t is a random process because it is a function of time, and it is, so y of t is a y of t is a random process, and now we would like to ask the question, is y of t, is it White's stationary, is it WSS or White's stationary? So, let us start with the mean or average or basically average of y of t. The average, in fact the time average mu y of t, which is the expected value of this random process y of t, is defined as follows, that is the expected value of minus infinity to infinity x of t minus alpha h of alpha d alpha. So, remember y of t is the convolution of x of t and h of t. Therefore, y of t is basically integral minus infinity to infinity x of t minus alpha, h of alpha, d of alpha, correct. And now we are taking the expected value of this whole thing, we are taking the expected value of this convolution between the random process x of t and the impulse response y of t. And therefore, now remember, since the expectation operator is linear, I can move the expectation operator inside this integral. So, this becomes expected value of x of t minus alpha, h of alpha, d of alpha. Now, remember that x t is wide sense stationary, x t is wide sense stationary. Therefore, it is stationary in the mean, which means at any time x of t minus alpha, the mean is basically the mean of this is constant, right. Therefore, this quantity is equal to this quantity equal to mu x, it does not depend on time. Therefore, what we have is the expected y of t equals minus infinity to infinity mu of x times h of alpha d of alpha. And now, since mu of x is a constant, I can bring this outside. This is mu of x times minus infinity to infinity h of alpha d of alpha, that is expected value of this random process y of t. And now, you can see that this quantity mu of x times integral minus infinity to infinity h of alpha d of alpha, this does not depend on the time. There is no time t in here, it does not depend, it is not a function of time. Therefore, this mean of this random process y of t, which is the output of the LTI system, is constant. Therefore, this is stationary in the mean, correct. So, this does not depend on time, you can clearly see it does not depend on time. Therefore, this is equal to a constant, that is mu of y, this is a constant. Therefore, the output random process y of t is stationary. The output random process y of t is basically stationary in the mean. And what do we have? We have the expected value of y of t is equal to mu y, which is basically a constant. Remember, this is basically, this is what, this is basically a constant. Expected value of y of t is basically demonstrated that for this output random process y of t, the expected value of y of t is basically mu y, which is a constant, it does not depend on time. Therefore, the output random process y of t is stationary in the mean. Let us now therefore look at the autocorrelation of this random process y of t. So, let us now examine, so we have demonstrated it is stationary in the mean. Let us now examine the autocorrelation of y of t, autocorrelation of y of t. We have y of t equals integral minus infinity to infinity x of t minus alpha h of alpha d of alpha as seen before. And let us consider y of t shifted by tau, that is y of t, y at t plus tau, that is equal to minus infinity to infinity. Well, x of, I have to substitute t plus tau instead of t, I am changing the integration index, this is only an index, h of t plus tau minus x of t plus tau minus beta times h of beta times d beta times d beta. Now, I have to look at what is the autocorrelation. Autocorrelation is nothing but the expected value of y t times y t plus tau, the autocorrelation of y of t, that is the correlation of y of t with a time shifted version, that is y of t plus tau. Therefore, let us now look at the autocorrelation of this. The autocorrelation of this is the expected value of y of t times y of t plus tau, which is equal to, now I have to write this, which is slightly long expression, which is the expected value of integral minus infinity to infinity x of t minus alpha h of alpha d of alpha, this quantity times the product times minus infinity to infinity x of t plus tau minus beta h of beta d beta, right, the expected value of y of t into y of t plus tau. I am simply substituting the expressions for y of t and y of t plus tau, and this is now the expected value of, now I can move the expectation, now I can move the expectation operator is linear. So, I can move the, first I combine the two integrals. So, I have minus infinity to infinity minus infinity to infinity the expected value of x of t minus alpha x of t plus tau minus beta into h of alpha into h of beta into d alpha d beta. Now, if you look at this, I have this factor of term type expected value of x of t minus alpha into x of t plus tau minus beta, and remember x is x t, the random process x is a wide sense stationary random process. Therefore, the autocorrelation depends only on the time shift or the time difference between these two time instants. Therefore, since x t is wide sense stationary, autocorrelation, that is, if we look at expected value of x of t minus alpha times x plus tau t x of t plus tau minus beta, this is the autocorrelation at t1 equals t minus alpha, t2 equals t plus tau minus beta. So, it only depends on, this only depends on the time shift between these two instants, t2 minus t1 between these two instants, which is equal to tau minus beta plus alpha. Therefore, this is here the expected value of x of t minus alpha times x of t plus tau minus beta is nothing but r x x tau minus beta plus alpha, right. The expected value of x of t minus alpha times x of t plus tau minus beta depends only on the time shift between these two time instants. Therefore, it is r x x of tau minus beta plus alpha, because x is a wide sense stationary random process. And now, substituting this in here, I have expected value of y of t times y of t plus tau, this is equal to this is equal to integral minus infinity. So, this is equal to integral minus infinity to infinity r x x of tau minus beta plus alpha times h of alpha times h of beta d alpha times beta of beta d alpha times d of beta. Now, you can see this whole thing depends only on the shift tau, that is expected y t into y t plus tau depends only on tau, that is the time, depends only on tau, that is the time shift. Therefore, I can denote this by r y y of tau, that is autocorrelation of tau, which depends only on the time shift tau, autocorrelation of y which depends only on the time shift tau. Therefore, it follows that y t is stationary in autocorrelation. Therefore, it follows that, remember, look at this, the autocorrelation of y t, the expected value of y t times y t plus tau depends only on the time shift tau. Therefore, it is stationary on the autocorrelation. Previously, we have shown that y t is stationary in the mean. Therefore, these two together demonstrate that y t is also a wide sense stationary random process. Therefore, y t is WSS. So, let me write this again here. Therefore, y t is a wide sense stationary random process. Now, further look at this, let me rewrite this again. I have the autocorrelation r y y of tau is equal to, I have, let me just write this over here clearly, this is equal to minus infinity to infinity, this is what is this? This is equal to, I am sorry, I am missing another integral over here. This has to be two integrals, one with respect to alpha, one with respect to beta. So, this is basically minus infinity to infinity r x x tau minus beta plus alpha into h of alpha into h of beta, h of alpha, d of alpha, d of beta. Now, let us do a simple thing, let us replace this alpha by alpha tilde. So, let us do the substitution, alpha tilde equals minus alpha. So, d alpha tilde will become minus d alpha. So, I can write this thing as integral minus infinity to infinity, integral minus infinity to infinity r x x. Well, the first integral with respect to alpha will now be from infinity to minus infinity, because alpha tilde equals minus alpha, the limits will become infinity to minus infinity, r x x of tau minus beta minus alpha tilde times h of beta times h of minus alpha tilde times d of beta times d of alpha tilde minus d of alpha tilde. Now, I have an integral from infinity to minus infinity, I have a minus sign. So, put these two together, then the integral will again become minus infinity to infinity, minus infinity to minus infinity to infinity r x x tau minus beta minus alpha tilde h of beta, let me write h of minus alpha tilde as h tilde of alpha tilde times d beta d alpha tilde, where h tilde of alpha tilde equals h of minus alpha tilde, that is h tilde of alpha tilde is h of minus alpha tilde. And now you can see from this expression you can now basically see, look at this Rxx tau minus beta times h of beta, Rxx tau minus beta minus alpha tilde times h of alpha tilde. So, this you can clearly see, this is basically a convolution between Rxx of tau convolved with h of tau convolved with h tilde of tau. So, this you can clearly see is the output autocorrelation, that is Ryy of tau is basically convolution between Rxx tau convolved with h of tau, that is impulse response, convolved with h tilde of tau. But remember, h tilde of tau is h of minus tau by definition, h tilde of alpha tilde is h of minus alpha tilde, therefore, h tilde of tau is h of minus tau. So, therefore, I can also write Ryy, what do I have, Ryy of tau equals in the time domain Rxx tau convolved with h of tau convolved with h of minus tau. This is the relation I have in the time domain, not exactly the time domain or the shift domain, the domain of the domain tau, that is a convolution in tau domain. So, this is a convolution, these are basically what are these are your convolution, these are your basic convolution operators. So, I have Ryy tau equals Rxx tau convolved with h of tau convolved with h of minus tau. Now, let us look at what happens in the frequency domain. To understand what happens in the frequency domain, let us look at what is the frequency response of h of minus tau. Now, if I look at the frequency response of h of minus tau, that is the Fourier transform of h of minus tau, let me call it, that is the Fourier transform of h tilde of tau, let me call it h tilde of f, that is equal to minus infinity to infinity h of minus tau e raised to minus j 2 pi f tau d tau. What is this? This is the Fourier transform of h of minus tau. Now, I substitute in this tau tilde equals minus tau, and this integral becomes, therefore, I have d tau tilde equals minus d tau. Therefore, this integral becomes minus infinity to infinity h of, well, minus tau is tau tilde e power j 2 pi f tau tilde d tau tilde, the d tau tilde, the negative d tau tilde, and the limits, remember limits become infinity to minus infinity, and then I am going to have a minus d tau tilde. So, this minus sign will go to the limits, and limits will again become minus infinity to infinity, and therefore, now I have, what will I have? I have h tilde of f is equal to this quantity. Now, if I consider h tilde conjugate of f, that is equal to minus infinity to infinity h of tau tilde e power j 2 pi f tau tilde d tau tilde conjugate, which is equal to minus infinity to infinity h conjugate tau tilde e power minus j 2 pi f tau tilde d tau tilde, but we are considering a system with a real impulse response h t. So, this becomes minus infinity to infinity h of tau tilde e power minus j 2 pi f tau tilde d of tau tilde, and this, if you can look at it, this is nothing but the Fourier transform h of f of h tau. We have integral minus infinity to infinity h of tau tilde e raised to minus j 2 pi f tau tilde times d pi tau tilde, and this is nothing but the Fourier transform of h of tau. Therefore, the Fourier transform of h of tau. So, we have h of minus tau, which is equal to h tilde of tau, whose Fourier transform is h tilde of f. This is equal to remember we have shown here that h tilde conjugate of f is equal to h of f, remember, which means h tilde of f is h of h conjugate of f. Therefore, we have h tilde tau, its Fourier transform is basically h conjugate of f. Why is that the case? Because this is because we have shown that h tilde of f conjugate is equal to h of f, which implies h tilde of f is equal to h of f conjugate. Okay. Now, if I substitute this in this, I have R x x tau, whose Fourier transform is the power spectral density of x, that is S x x f, times, remember, convolution in time domain or tau domain implies multiplication in the frequency domain, times h of f, which is the frequency domain, times the Fourier transform h of minus tau. We have shown this is h conjugate of f, and this is the power spectral density S y y of f, that is equal to S y y of f. It is the power spectral density of the output random process y of t is S x x of f, the power spectral input power spectral density, or power spectral density of the input x, times h of f, the frequency response of the LTI system, that is the Fourier transform of the impulse response h of t, times h conjugate of f, that is the conjugate of the Fourier transform of the impulse response h of t. And now you can see h of f times h of conjugate of f is nothing but magnitude h of f square. Therefore, we can write net, I can write, which is a very interesting result that I have for the power spectral density. I have S y y of f equals S x x of f times magnitude h of f square. I have magnitude h of f square. So, therefore, I have, so this is my output PSD, this is the PSD of the output, this is the input PSD, input power spectral density, remember PSD stands for power spectral density, and I have, this is the magnitude of, remember h of f equals is the Fourier transform, h of f is the Fourier transform of h of t, h of f is a, so this is the magnitude of h of f square. So, what we have shown is that the magnitude, that is the output power spectral density S y y of f is equal to the input power spectral density S x x of f times magnitude square of the Fourier transform of the channel response, of the channel frequency response, that is magnitude h of f square. And this is a very interesting result and a very important result which relates the input of random Whiteson stationary random process to the output Whiteson stationary random process. So, we have demonstrated something very interesting. We have considered the transmission of a random process Whiteson stationary random process x t through an LTI system, which is characterized by an impulse response h of t. We have shown that the output random process y of t of this LTI system is itself whites and stationary, with stationary in the mean, stationary in the autocorrelation, and further we have demonstrated something very interesting, that is the output power spectral density SYY of f is the input power spectral density SXX of f times magnitude of h of f square, where h of f is the frequency response of the LTI system, that is h of f is the Fourier transform of the impulse response h of t of the LTI system. So, we will stop this module here and we will look at other applications of this in the subsequent modules. Thank you very much.